Morning, good afternoon, good evening, everyone. Thank you for joining us today. Welcome to this webinar, which is part of the ongoing series hosted by ISO Technical Committee 347, Data-Driven Agri-Food Systems. My name is Andres Ferreira, and I'll be your moderator for today's session. This webinar series is designed to explore key technical areas where standardization can support innovation, sustainability, and interoperability in agri-food systems. Today's topic, reference data, master key to data-driven agri-food systems, presents the fundamentals of reference data in agri-food systems information management with numerous examples. It also describes the work that TC347's Ad Hoc Group 2 has performed over the past 15 months, preparing a draft standard and a new work item proposal for a data model for crop definitions. This is the first in an upcoming string of high-impact semantic standards and an enabling technology that will help connect diverse actors from farmers and researchers to technology providers and policymakers. ISO TC347 is a new and ambitious committee that's working on developing international standards that enable trustworthy, inclusive, and effective use of data across agri-food systems. The webinar is part of our commitment to transparency, engagement, and inclusive participation in the standards development process. Today, we aim to introduce the key technical insights related to the topic of reference data in agri-food systems. We also aim to highlight how this topic connects to standardization opportunities and show you how you can actively participate in shaping upcoming international standards. So we're very fortunate to be joined today by Stuart Rhea and two guests who will lead us through today's discussion. Stuart Rhea has a bachelor's degree in chemistry and computer science and a master's degree in physical chemistry. He worked as an embedded engineer developing portable analytic instrumentation for 8 years, then transitioned into agricultural data integration. For the past 18 years, he's worked on a variety of complex data integration, architecture, and strategy projects, first in AgConnections, a farm management information system software company, then in Syngenta, and more recently at Verity. Since 2010, Stuart has been actively involved in international standardization efforts, especially in Ag Gateway, an agricultural industry nonprofit data interoperability consortium, where he has co-led the technical committee of ADAPT, the Agricultural Data Application Programming Toolkit, for nearly a decade. So with that, I'll now hand things over to Stuart Rhea to begin the presentation. Stuart, the floor is yours.
Thank you. Good morning, good afternoon, good evening. As Andreas said, I'm Stuart Rhea, convener of TC347's Ad Hoc Group 2, Model and Controlled Vocabulary of Crops. And I'd like to take a few minutes to tell you about our work in TC347. A few years ago, ISO convened a strategic advisory committee on smart farming to survey existing agricultural standards and identify gaps. The resulting report included a number of recommendations, one of which was the formation of this TC. Another identified the reference data and the semantic resources to manage it as a critical component in enabling interoperability. And finally, the development of this data model for crop. While reference data is important across our whole agri-food data ecosystem, I draw your attention to a specific subset, field operations data, because it makes for a practical illustration. This is a specific area where interoperability has been a persistent problem. As a concept, interoperability is usually broken up into two parts. First, syntactic interoperability, which is related to how the data is structured or shaped. You might think of this as the format of the data that you're receiving. And then semantic interoperability, which is related to the meaning of the variables or other controlled vocabularies that are used to encode the data. Our work is focused on implementing this semantic interoperability by establishing standards. The controlled vocabularies used in expressing field operations data usually falls into three categories. First, reference data, which is the subject of this webinar, has a global scope. It represents uniquely identified concepts or classifications that mean the same thing everywhere. This, comes in the form of lists of crops or lists of pests or active ingredients. Then we have setup or master data, and this has a narrower scope, usually around a specific grower or a business entity. It represents the set of uniquely identified resources that are used in planning or executing tasks. Think, the list of farms or fields and the boundaries of those fields. All of these things are controlled vocabularies. They're just very specific that particular grower or that particular business entity. And then finally, there's configuration data, which is scoped to the state of the resources that you're using at the time of their use. So in this case, it would be how your planter is set up if you're planting corn versus planting wheat, right? Those two sets of parameters are usually stored digitally, and that's configuration data. So all of this, right, this documentation kind of cycle that you see here, all of this reference data and setup data and configuration data, all of it serves to underpin the cycle of principled decision making that we're showing here. Crop was selected for development because of its foundational place in our data ecosystem. But it's only the first in an expected series. It's a particularly challenging one since crop as a term it is often understood differently based on context. For example, when you go to search for a seed product, what are you asking? Well, show me all the new corn seeds or corn varieties for this year. Or maybe to classify land usage. Where are all my wheat fields? Or finally, to describe a quantity of harvested material. Is that the last pallet of cherry tomatoes? So, this heavy reliance on context in order to understand what you mean by crop results in a lot of ambiguity and often unstated assumptions that have a big impact on interoperability and on data quality in general. Our process of collecting diverse use cases, 16 at the current count, has shown that different stakeholders have different needs for level of detail. From the perspective of a machine, the level of detail needed could be very general. Wheat or corn selected from a drop down menu is good enough because, in addition to classifying the collected data, it sets sensor calibration values. But from the perspective of, say, a risk manager trying to write a crop insurance policy, the level of detail needed is much more specific. 40 acres of organic sweet corn for fresh market versus grain corn being grown for animal feed are likely to have quite different premiums that have to be paid. Therefore, we need a model that allows crop definitions to be as general or as specific as the situation demands. In our review of existing sources for crop vocabularies, we found two very interesting things. First, that many of these vocabularies blend in other aspects, like intended usage of the harvested material or additional details about growing methods, along with the genetic or taxonomic information. And second, that supporting crop groups is important for enabling practical applications, like automated label checking, which is something Patricia will tell us a little bit more about shortly, and mapping among vocabularies of different granularities. So now that I've described for you some of the model requirements our discovery work's uncovered, I'd like to show you the model that we're proposing. We're using a faceted component framework to model crop as a composition of discrete particles of meaning. The characteristics that contextualize a crop are represented as orthogonal or non-overlapping refinement categories. Think of these as mini controlled vocabularies. Each refinement category is independent of the others. The The variation in one category doesn't imply or constrain the values of another. These categories enable the creation of crop definitions that are tailored to both general and highly specific needs without overloading the concept of crop with hidden assumptions. This model enables semantic precision where we need it, flexibility to grow and expand over time, and most importantly, machine actionability, because the meaning is baked into the series of components, not baked into a single label. You see here the UML that illustrates it. Let's walk through a specific example. So we start with the crop definition object itself, right? That object has a code, which is a shorthand way of referring to this object. It has a persistent identifier that might be a URI that you can resolve. It has a description that's simple and straightforward, but then it has two additional pieces. First, we start with the taxon, the botanical or genetic aspect of the crop that we're trying to target. Each species can be linked to a global taxonomy of identifiers. So think about, EPO codes for the species. Remember that we're treating this genetic information separately as taxon for a person. It's kind of the primary discriminator that we're working against. Then we have the crop refinements, right? These refinements come from categories, each category being a little controlled vocabulary of its own. So in this case of soft red winter wheat, we have this refinement category of color, red, white. We have a refinement category that's related to the physical characteristic of hardness. So soft to hard white winter wheat versus soft red winter wheat. And then finally, growing season. So building up meaning from these discrete components allows us to do a lot of interesting things, including querying for show me all the wheat crops that are in the system. Well, we query based on the taxa that's present. This gives us a lot of configurability, a lot of ability to expand because we can define more crop refinement categories as we need. So things like the part of the plant that's being cultivated, whether it's for the fruit or the stem like sugar cane or the root like a carrot, these things can be specified as crop refinement, a crop refinement category. As I said before, crop was selected for development because of its foundational place in our data ecosystem. As you can see here, we've got other vocabularies to tackle, and they build upon crop. Field operations and pests both lead towards building on crop. Phenological stage, both for the pest and for the plant itself. And all of these things all of these controlled vocabularies need a place to live. And that's where we get to our semantic resources that the SAG report pointed out needed to be developed. All of this is useless without a central repository where these controlled vocabularies can be curated and made available for use. As a part of this work, we're working to create a maintenance agency to serve as a custodian and registrar, not only the controlled vocabularies, but also a corresponding mapping service that will support a system of managed crosswalks. What I'm most excited about is the practical application of this standards work. And so I'm happy now to turn this over to Patricia Perez, who will tell us a little bit about how her organization works with reference data to operationalize things like our crop model. Patricia, over to you.
Thank you, Stuart, and good day, everyone. What we just presented depends on a common language, and that's what I want to focus on, why reference data and control vocabularies are the key to that shared language. At LexAgri or Food Chain ID through the Homologa database, we process thousands of plant protection product labels together with agricultural reference data, commodities, trade, growing statistics from FAO and registered seeds worldwide. When you start reading these labels and this scattered agriculture data, you realize that even though they look similar, they speak completely different semantic language. Here's a real case. The plant protection product called Cevia, the same fungicide registered in Canada, Peru, Chile, and the US. Each label contains the same type of information, but expressed in completely different ways. The chemistry is identical, the company is identical, but semantically, there are 4 different realities. The ambiguity breaks interoperability. Control vocabularies remove the risk. Every symbol, unit, or code carries one clear meaning. We all want digital agriculture to scale, but without a common language, that becomes noise. Here you see the comparison summarized, 1 molecule, 4 interpretations. Without harmonized vocabularies, digital agriculture cannot scale. In ISO TC 347, we are going to provide the reference data framework that let us align these expressions so many machines and humans interpret them in the same way everywhere. And ambiguity doesn't stop with the crop or the active ingredient or even the pest. I have chosen here one of multiple examples I find. Those rates expressions differs by application environments. Reference data establishes a common meaning and converts every unit to a canonical standard. Here is defining whether we are on the field, we are on a greenhouse, or we apply to seeds, or on traps, or biocontrol products. Here we speak about semantic interoperability in practice. In the next 2 slides, I will show what a harmonized label structure looks like. Every field of data, from product name, formulation, active ingredients, restrictions, etc., can be standardized when we apply reference data. In the first part, we have the product. And let's speak about formulation types. We have EC, SC, WG. Those must be linked with a control vocabulary. As it happens with countries, we have them standardized on ISO so that every database knows what it means. Then we have active ingredient. The mode of action as another of the key control vocabulary we have shown previously and essential for resistant management, strategies, and sustainable use. To finish with the use restrictions, when a label shows 0 as a PHI, does that mean there is no waiting period? Or when we show a dash, does it mean not applicable? This structured approach eliminates misinterpretation and enables true semantic interoperability, not just sharing data, but sharing a meaning. And finally, the same logic applies to target and growth context. We standardize crop names and their growth stages. We use control vocabularies for target, pest, effect, so that when the label says wireworms, we all know exactly which organism it refers to. Phenological stages, time of application should also be linked through standardized reference data. To finalize, application methods, ground, aerial, broadcast, directed, is spot directed, etc. Vocabularies make these distinctions clear and machine interpretable. This removes ambiguity and ensures that when one system exports data to another, they are all speaking the same structured language. And now, to answer the key question, how do we define the crops and crop groups? I hand over to Monty.
Good day, everyone. And Patricia, thank you so much for a very, very good introduction to the concepts of structured vocabulary and control groups. My name is Monty Dixon. Worked in the ag industry, primarily in crop protection for almost the last 40 years with Ciba Geigy, then Novartis, Syngenta, and now. I've worked in roles as a metabolism chemist, but really for the last 25 years have been working in the regulatory space. And so much of what Patricia just described is something that I have found has been a very important area and need for us to focus on getting some standardization on. I'm only going to talk about one element, which is crop groups. And I'm going to come from a very US specific background because that's my experience, but it's certainly extrapolatable to the entirety of all of agriculture throughout the world. So just in the US alone, if we think about what crop groups, well, one more slide, please. There's over 600 individual commodities currently listed in the U.S. Code of Federal Regulations as crops. They're broken down into 26 crop groups. Many of those have subgroups, and each of the subgroups consist of representative commodities, which are used for extrapolation to the overall group, and the member commodities. Crop groups are put together based upon sets of botanically and agronomically related characteristics. Ultimately, these characteristics are what contribute to similar pesticide residue patterns. These are used by regulatory agencies such as EPA, USDA, Codex. These allow for streamlined pesticide tolerance evaluations, and as I'll mention a little bit later, tolerances are really used as a key element of determining safety profiles. Some general examples are crop groups known as the leafy vegetable group, and that group consists of many members, but the representative crops would be lettuce, spinach, and kale. Same thing for the citrus fruit group. There's many members, but you have representative commodities of orange, lemons that represent the remaining membership of the group. You have fruiting vegetable group that would have, for example, tomatoes, peppers, eggplant. The benefits of this is that by using crop grouping, you're allowed to have regulatory and research efficiency. So as we think about the selection criteria for what brings things into crop group, it really comes down to the behavior of the crops within the group. One of the key elements is how does the crop group interact with exposure to the pesticide residue? Would it have the same metabolic profile? Will it have same growing conditions, same temporal, same regional growing conditions? What about the morphology? There would be a significant difference, for example, from a leafy crop versus a root and tuber crop. By using the ability to group these member components of the crop groups together, you're allowed to use extrapolative processes so that you don't have to test every single member of a group. That would be both economically and logistically impossible. There's not enough laboratories to do the analysis, and the regulatory agencies in and of themselves would not have the resources to be able to look at data for every single individual member of a crop group. Therefore, they use these characteristics of the grouping to allow them to extrapolate to other members. By using this, the agencies are able to set pesticide tolerances more efficiently, and this allows for the use of these tolerances for risk assessments as well as import and export purposes. Ultimately, it allows for regulatory decisions that are both scientifically sound and resource efficient. As I just mentioned, the key elements for structuring crop groups is around their morphological similarities as well as their similarities in how they respond to exposure to pesticides. There's the cultural practices, which also play a crucial role. Other elements that play important roles are what are the edible portions of the crops? How are the crops being used? Are they being used for potential use in feed and for livestock? Or perhaps it's just a crop being grown for seed. All of these different characteristics then come together into how one might use crop group. Ultimately, you also have to take into account the different geographical implications of crop groups. What are the growing seasons? What are the soil types? What are the characteristics that might somehow influence the pesticide behavior within an individual crop? Regulatory agencies like EPA use crop group data to set pesticide tolerance, which are also known as MRLs, and these are critical for the ability to actually import and export crops from different countries. By applying the pesticide data from these representative crops and establishing the tolerances, they are allowed to more efficiently do risk assessments. Instead of having to assess each individual crop, they can do it within the crop groups. This also allows for them to use this same type of data and information to do risk assessments, say, for example, on dietary exposure, as well as aggregate exposure. So what would be the potential risk from exposure from multiple different sources of pesticides? This allows for a holistic assessment of the public health impacts of using these products on crops that would be ultimately into the food chain. This tolerance setting and risk assessment allows for a robust scientific evaluation to make sure that the use of these products is both protective and efficient and allows for sustainable agricultural practices. Ultimately, and one of the things that has changed so much in my 40-year career is the importance of international harmonization. By using crop groups, working through efforts of folks such as the Codex, NAFTA Technical Working Group, OECD, we're able to have consistent MRL standards. This allows mutual recognition of residue data. As previously mentioned, reduces the need for redundant testing requirements and provides a clear regulatory framework across the different marketplaces in different countries in which these crops might be exported and imported to. Harmonization makes it possible to reduce the technical barriers to trade, but also ensures we're able to maintain safety standards.
Thank you, Monty, and thank you, Patricia. So what comes next? TC 347 Ad Hoc Group 2 has finished preparing their new work item proposal and a draft of the standard. Now, understand that this is a working draft. This will be submitted as part of our Form 4. It'll go into the NP ballot before the end of the year. This working draft includes our 16 use cases, one of which is the automated use of digital product labels, of being able to tell for a given field where a specific crop is planted, whether you can use a product or not, and what rate you should use it at. It also describes the data model and goes into detail about how the different parts of the model are intended to work. It has a number of encoded examples in it as well. The intention here, as we've seen in some of the previous slides, is that crop is the precursor, is a forerunner for a series of standards around different controlled vocabularies that the industry needs. So the intention is to create an agrisemantics working group within TC 347 to develop this string of reference data standards. And I would love for you, all of you, to join us in this work. And with that, I'm going to pass it back to our moderator, Andres.
Thank you very much, Stuart, and Patricia, and Monty as well. You've covered some great material. It was very enlightening. We'll certainly dive a little deeper into these things with the questions. So let me just share a little bit about how TC 347 works. We have plenary meetings, and then we have our subgroups. The plenary meetings are when we all get together, everybody in the technical committee, and these happen twice a year. We have one in the fall, which happens tomorrow and the day after, and we have one in the spring, which is face-to-face. The fall one is virtual. Now, we use these plenaries as a way of all getting in sync and understanding what's going on and what each one of us is doing and where there's opportunities for tighter collaboration. But most of the work happens inside our subgroups, like, for example, this ad hoc group 2 that Stuart mentioned. So we have ad hoc groups, we have advisory groups, and as our standards get balloted, or our new work item proposals for standards rather get balloted, we start forming working groups to finish developing those standards in. There's two ways of contributing. One is through your national standards body. So your country will have an organization that represents it in ISO, and that organization may take upon itself organizing what's called a mirror committee into Technical Committee 347, or it may decide to delegate managing that mirror committee in another standards development organization. If you're interested and you don't know who the standards development organization that manages the Mirror Committee is in your country, reach out and we'll help you find out. The second way of participating is through a liaison organization like AgGateway, AEF, ISPA, and several others. Check in our main ISO page that you have the link to right there to learn more about what our liaison organizations are. Finally, please contact us. If you have any questions, reach out. We have an email address there for you. We also have a LinkedIn page where we share interesting information, and that main ISO page that I just also mentioned. So now let's transition into questions. I have a first question before we take questions from the group. If I had to give a first answer to where the value of this is, for example, in that sequence, that string of early standards that you mentioned, is to be able to enable technologists to develop tools that can help producers, right, to maybe stay out of trouble. And I can imagine several examples, like, for example, managing active ingredient loads or managing pest resistance. So let me ask Stuart and then Patricia. Stuart, could you explain, for example, how this reference data can help manage active ingredient loads? And Patricia, you then answer how modes of action and resistance management can be handled.
Sure. So things like active ingredient load, right, and being able to calculate that. And let's explain just for a second what that is. It's basically the thing that kills the pest that you're targeting is the active ingredient. And so each active ingredient has certain limits in which they need to be used within a given span of time on a particular field. And sometimes these active ingredients, right, they act on the plant itself. Sometimes they act on the soil. So there's a big variance in how much of a particular active ingredient is okay to use that doesn't damage the soil and it doesn't damage the plant. So being able, because you know for a product how much active ingredient is there, and then from your field operations records, you know how much you've used on a particular area, then you can add up over a given period of time how much active ingredient was there. And so you have a number of controlled vocabularies that are in play there, not only the list of active ingredients, but also, which field you're talking about, also which crop you're targeting. So it illustrates very well the practical application of these controlled vocabularies, because if you don't have that standardization in place, right, if product X doesn't mean the same between system 1 and system 2, records coming from system 1 and system 2, then you have no real way of knowing and being able to add those values up. And I will happily defer to Patricia because she knows much, much more than me about that particular subject.
About active ingredients, I think you describe it very well. But when you have active ingredients, what is important to have a common language and semantics? Because behind an active ingredient, you have a lot of information to do analysis. And I spoke before about the mode of action that gives the answer to resistance. You have to apply more than at least three different mode of actions to avoid resistance, and you can exchange with biocontrol or different multi-site active inhibitors. And to analyze through the mode of action, if we have this common semantics behind the active ingredient, you can do more sustainability and analyze to avoid resistance in your field.
Well, if I may add one piece to that too, it's very much builds into the importance of risk resistance management that Patricia was mentioning. We've seen a significant shift to multiple AI containing products now, sometimes 3 and 4 different AIs and modes of action. So this would really be a key element for allowing people to get that maximum load that Stuart's indicating across multiple products that have different AI concentrations being applied at different rates.
Thank you. We have a question that Patricia answered in the chat. The question had to do with this very, very slippery concept of application method, right? Which is one of those things that looks simple, but then it gets complicated rather quickly. He mentions that plant protection product registration usually deals with application method in a very inadequate way. And the EPO codes that were mentioned, the European and Mediterranean Plant Protection Organization codes for these things, formerly called Bayer codes, by the way, he mentions are a good example where the only way of the spraying application listed is called an air blast sprayer, which only describes a very specific kind of thing called an air blast, and does not represent many other approaches. So he asks how can we work seriously in the context of having such an inadequate input vocabulary, right? And then Patricia answered, yes, you're right. I see that existing vocabularies for application methods like EPO are too limited to describe the diversity of real equipment and conditions. We, in her case, LexAgri, the company that Patricia works for, often have to enrich those terms manually or map them to more detailed internal classifications so they make sense across regions. This is exactly where I believe that ISO TC 347 can add value, by creating a framework that connects and extends existing vocabularies instead of replacing them. And in the spirit of full disclosure, Patricia and I have spoken before, I being the chair of TC 347, about how application methods are another one of those building blocks that we need to add to our string and work with Technical Committee 23, Subcommittee 6, for example, to make sure that we get that list right. And for that to make any sense, you have to work with and engage a broad spectrum of stakeholders so that the list is relevant and has a shot at getting used. But the approach that Stuart and his team have followed regarding componentization of these codes allows setting up mappings among them, right? So that you can set up this sort of Rosetta Stone that can allow using codes from companies that already have their sort of entrenched vocabularies and be able to interoperate with one another. Stuart, can you elaborate a little bit on that concept of crosswalks that you mentioned earlier?
Sure. So in addition to setting up this framework of crop as a controlled vocabulary, one of the other things we've identified as being essential is accepting the fact that there's tons of historical data out there, right? Expressed in other controlled vocabularies. And that stuff is just not going to go away. And there's just not going to be this massive overnight shift from everybody's individual vocabularies that they're using into, one to rule them all. That's just not going to happen. It's not realistic. So what do we do in response to that? Well, we set up this framework of being able to have an emergent kind of global controlled vocabulary of crop, where we seed it and we start by putting in entries that are fairly common. And then we encourage people to add new entries that become increasingly more specific. And we facilitate this interoperability by providing a mapping service that lets you assert equivalencies between things in external vocabularies and entries in the new central registry, right? And being able to make those assertions and record who makes those assertions and have the service be able to let you look up. If we have a crop list from John Deere, right? And John Deere dedicates somebody to mapping their crop list into the new kind of global standard vocabulary, that mapping made by the company itself probably holds more weight than mapping made by some random person, right? So not only is there the need to support this mapping as a service, but also to have it, curated and be able to manage it really well. So this kind of is going to empower kind of a crowdsource approach of having these crosswalks available, and we grow the central vocabulary at the same time that we're enabling interoperability with the use of these crosswalks.
Thank you, Stuart.
Sure.
Our audience is starting to ask more and increasingly
Bring it on.
interesting questions. So Kevin and Annika asked two aspects of sort of the same question, right? So Kevin mentioned that or asked if there's a concept of event recording. So like what was applied where and when, in what quantity to back up pesticide load numbers, right? And so there's a standard called ISO 11783 Part 10. It's managed by Technical Committee 23, Subcommittee 19, which is Agricultural Electronics, a committee that we have a very good working relationship with. And that standard enables the recording of the operating parameters of a field operation of any sort. Stuart would tell you that a problem with that is that product identification is usually rather poor, right? And so if you just have a record that some stuff was sprayed at a certain rate, and that stuff, typically called product one, the most widely used product in the universe, right? Usually applied to field one also, by the way. That isn't sufficient, right? And so he has led work in a group called ADAPT to be able to enrich that. And Patricia, actually, who's with us, is leading, together with Connie Graumans from the Netherlands, our ad hoc group 8 on digital land usage history, which is a way of representing a sequence and relationship between the observations that you made in the field, the recommendations that somebody made, the work orders that somebody made about that, and the field operation itself and its results, right? And to Annika's question of what does this have to do with product passports? Well, an alternative way of looking at digital and land usage history is to call it a field passport, right? Which is keeping track of all the things that you did. So, Patricia, do you want to say a couple words about that?
Yeah, I just answered Annika in the chat. We are working on it. What is a digital passport? What is a crop zone? What is a crop? All of those questions will be with an answer. What is needed to create a digital passport? It's the same in the same day that the product passport created on the Green Deal. And we are going to define, we are in the modeling of the data to arrive to the digital passports. And it's complex, but I hope we are going to achieve it.
Thank you, Patricia. And to Petri Lina's question about European Union data spaces and what our relationship with that work is. So certainly Europe is a very important source of requirements for us because they have a very active um, set of activities in regulating things that have to do with agriculture. And very often what they do today is what everybody else is doing tomorrow, or at the very least, like say in the case of the European deforestation regulation, it it can propagate a lot of impact across the industry worldwide. So we created an advisory group inside our technical committee led by Professor Benjamin Beinacht uh, to deal with regional matters initially, especially in Europe, that is tracking and establishing relationships with these kinds of groups. So we're aware of the European work on data spaces, and we're looking to establish a relationship with it because the life's too short to reinvent the wheel, frankly. Let's see what else. What other questions do we have? Ability to have robust application records is important for many reasons, and these are certainly enabled by this type of work. There's sometimes legal and other considerations that complicate this. For example, who owns the application data? Is it the grower, the applicator, etc.? So that's a very good point, right? When you're talking about data ethics. Um, these are not exactly orthogonal concerns. So who owns this stuff isn't completely independent of how you represent the data, right? But they're often complementary concerns because regulators determine in a given jurisdiction who owns the data, not people who are coming up with data formats and so forth. Stuart, you led an agricultural data ethics effort recently in Ag Gateway. Do you want to add anything to that?
Just that, it's something that's top of everyone's mind, especially when you start bringing in the usage of data in the context of AI and having the appropriate permissions in order to use such data to do things. And in the end, I think the thing that we landed on in the white paper that we developed is primarily the principle of informed consent and of the obligation of data exchange partners, whoever they might be, however big or however small, to be honest about indicating what they plan to use data for and be upfront about it. Right? There's nothing that people are going to try to legislate this stuff. Yes, there are those that get taken advantage of versus those that do the taking of advantage. But in the end, it becomes a matter of informed consent. And if you are allowing your data to be used and receiving in return the ability to use a piece of software or use a system at a discounted rate or at no cost, that's part of the bargain that you make. The key findings in our paper were, hey, let's just be upfront about it. That's the hallmark of a good neighbor and a good actor in this space is informed consent and full disclosure.
Two quick notes about TC347, and then we pivot to the next question. One is that we do have a group in TC347, which is our advisory group 3, led by James Lowenberg de Boer, about responsible innovation in general, which will, I think, cover the idea of data ethics by design as well, right? So this is something that we're aware of and looking at how to create guidelines. In fact, we're launching our first version of a guidelines document this week at our plenary about how to be able to think about the consequences of possible adverse consequences of the standards we develop. That's one thing. The other thing is that in our strategic business plan, we do have as a strategic objective to develop a standard for a notation, a symbology of sorts, to be able to simplify the interpretation of data sharing contracts so that the implications of the contract language to the user can be made clearer through icons or something like that. So if somebody's interested in that, we'd love to tell you more. Pivoting to another question that I think I saw here. Oh, yes. So somebody asked, let's see who it was, Andrew Moxie asked, would a field passport account for within field variation? I'm thinking about things like buffer strips, beetle banks, and other less intensively managed portions of fields. That's a fantastic question, right? And I know that that Patricia mentioned that that's rarely a homogeneous concept, right? It's a great way to segue into the fact that we recognized that agricultural management happens at many scales, right? And sometimes you're thinking about the whole field, but sometimes you're managing that field differently, right? And so in the data model that we've been looking at for doing this, there exists the concept of a crop zone. Stuart, do you want to mention that a little bit, how that works? A 1 minute intro, because we've got 1 minute left.
Sure, sure. So, a field typically is defined as whatever a grower wants it to be, right? Maybe it has certain spatial extents, maybe it's just a label. Andreas referred to field 1 as being the most commonly used field in all of agriculture. We settled on something that's somewhat analogous to ISO 11783's part field, which allows you to say, okay, in this spatial area or this area, during this time, this is the crop that's being grown. And then your application records, all of that stuff is applied to that crop zone, right? But it's very tightly scoped, both in space and in time, so that it helps you essentially keep your records together, your application records together in a way that lets you make a very specific statement, not only about that piece of land, but also about the harvested material that comes off of it, right? Because you are scoping it to, I planted this, organism, and I'm pulling this material off. And all of that occurs in this time and space scope that's very well defined. So I might have gone over just a little bit of a minute there.
Thank you, Stuart. I was just putting into the chat that for anyone who's interested in this crop zone concept further, it's defined in a document called ISO 7673 Part 1, which is currently sort of a ghost document because it's been pulled so that we could add maintenance agency information to it. So soon it'll pop back in. But if anybody's very interested in that, just let me know and we'll hook you up. So we've had 3 great presenters at the top of their game telling us about how reference data for both product and non-product information can help make data interoperability more scalable than it currently is. We had some great questions. This is the line of work that will probably be balloted first in TC 347 and become a very active agrisemantics working group in just a matter of a few weeks. So I would invite you all to take a look at TC 347, look to join this effort, and again, thanking all our speakers and the audience. I think we are adjourned for the day. Thank you.